The long-standing assumption that stealth ensures control of contested airspace is no longer supported by engagement modeling or operational data.
The foundational assumption that stealth would indefinitely preserve air superiority is no longer supported by observed performance data or doctrinal modeling. For 4 decades, modern air combat doctrine has treated reduced observability as the decisive attribute in penetrating defended airspace. The post-Cold War consensus held that survivability derived primarily from avoiding detection long enough to deliver precision weapons before a defender could respond. Stealth aircraft were therefore not merely platforms, but organizing principles around which sensors, command structures, and strike packages were designed. This consensus emerged from a specific technological moment in which radar systems struggled against low observable shaping and materials, and in which missile kinematics placed practical limits on reaction ranges. The result was a doctrinal framework that equated invisibility with initiative. That framework is now under structural stress. The rise of missiles as the dominant air combat solution began in the latter half of the 20th century, when guided weapons replaced guns as the primary means of aerial engagement. Surface-to-air missile systems expanded defensive envelopes from visual range to hundreds of kilometers, while air-to-air missiles transformed fighter engagements into contests of detection and first launch. This shift reorganized force structure. Aircraft became launch platforms optimized for sensor fusion and weapons carriage rather than close maneuvering. Ground-based air defense networks matured into layered systems designed to create overlapping engagement zones, with radar acquisition feeding tracking systems that cued interceptors. The missile became the arbiter of air control, and both offense and defense were calibrated around its performance envelope. Missile systems, however, are bounded by physical ceilings that doctrine often treats as flexible margins rather than hard constraints. Every missile operates within a defined energy budget determined by propulsion burn time, mass fraction, aerodynamic drag, and thermal tolerances. After motor burnout, the missile enters a purely ballistic or semi-ballistic phase in which it trades altitude and velocity to maintain maneuver authority. Maximum range figures assume optimal launch conditions, cooperative geometry, and limited evasive maneuver by the target. As target speed increases, closure rates change, no escape zones contract, and guidance correction windows narrow. What is often described as a nominal engagement envelope is in practice a rapidly shrinking cone when confronted with extreme velocity. As aircraft speed increases beyond traditional subsonic and low supersonic regimes, a paradox emerges. The same missiles designed to defend or equip those aircraft become less effective against them. Cause precedes mechanism. When an aircraft operates at significantly higher Mach numbers, it compresses the time available for detection, classification, tracking, launch authorization, and missile flyout. The mechanism is straightforward. Increased velocity reduces both intercept geometry stability and guidance update intervals. The operational effect is that a defender's engagement sequence must be completed in a fraction of the time originally assumed in doctrine. The strategic consequence is that defensive density no longer guarantees denial of access. Speed begins to erode the reliability of missile-centric control. Propulsion is central to this shift. Traditional turbojet and turbofan engines provide sustained thrust within predictable thermal envelopes, optimized for endurance and payload. High-speed flight at sustained supersonic or hypersonic regimes demand alternative propulsion concepts and structural tolerances capable of withstanding extreme aerodynamic heating. At high Mach numbers, skin temperatures rise dramatically due to friction and shock compression. This heating alters infrared signatures, but also affects material integrity and fuel efficiency. Energy management becomes not simply a matter of thrust, but of altitude selection and trajectory shaping. Aircraft operating at high altitude in thin air can maintain velocity with reduced drag, converting potential energy into sustained forward momentum. The higher the initial energy state, the less vulnerable the aircraft is to interception. Altitude compounds the effect. At extreme altitudes, radar horizon geometry shifts. Ground-based radar coverage becomes limited by line-of-sight constraints, while atmospheric density reductions complicate missile lift generation. A high-speed aircraft operating near the upper bounds of controlled flight exploits these physics. The mechanism is not invisibility, but outrunning the defender's decision cycle. Operationally, defenders must detect earlier and react faster. faster, yet detection reliability often decreases at extended ranges due to clutter, atmospheric effects, and signal attenuation. The strategic consequence is that defensive planning margins collapse simultaneously in time and space. Thermal considerations further complicate interception. High-speed platforms generate significant infrared signatures due to aerodynamic heating, potentially improving detection by infrared search and track systems. However, detection alone does not equate to engagement success. The defender must still generate a firing solution, allocate a missile, and achieve intercept geometry within shrinking timeframes. The mechanism here is temporal compression. Even if a target is detected earlier, the time between detection and target exit from engagement range decreases. Operationally, command authorities face accelerated launch decisions with limited confirmation windows. Strategically, the reliability of layered defense becomes probabilistic rather than assured.
As speed increases, interception timelines begin to collapse in ways that undermine established procedures. A layered air defense system traditionally relies on sequential engagement opportunities: long-range detection, mid-range tracking, interceptor launch, and terminal guidance. Each layer provides redundancy. Extreme target velocity disrupts this sequencing. By the time a long-range radar confirms track quality sufficient for engagement, the target may already be within or beyond optimal intercept geometry. Missile flyout time becomes a liability rather than an advantage. The faster the target, the shorter the engagement arc during which the missile can maneuver effectively. The operational effect is a reduction in effective engagement depth. The strategic consequence is a thinning of defensive resilience. Fighter aircraft face a similar constraint. Air-to-air combat doctrine presumes that fighters can maneuver to favorable positions, supported by airborne early warning assets and data-linked targeting. Against a high-speed intruder, positioning becomes constrained by geography and fuel. Interceptors may be airborne yet unable to achieve closure before the intruder exits contested airspace. The mechanism is simple kinematics. If the speed differential is insufficient, intercept becomes geometrically impossible without forward basing or predictive positioning. Operationally, this forces defenders to maintain constant high-readiness patrols at extended cost. Strategically, it shifts the burden from reactive defense to persistent forward presence. Surface-to-air missile systems are equally constrained. High-speed targets reduce radar dwell time and increase Doppler filtering challenges. Tracking algorithms must discriminate rapidly moving objects from background clutter while updating guidance commands at accelerated rates. Even with advanced active seekers, terminal phase maneuver authority may be insufficient against a target that retains high residual energy. The cause remains speed-induced compression of engagement windows. The mechanism is energy asymmetry favoring the intruder. The operational effect is reduced probability of kill per missile. The strategic consequence is increased expenditure rates and uncertain denial capability. Sensor networks experience parallel strain. Integrated air defense relies on distributed sensors sharing track data through command and control nodes. Data fusion requires processing time, correlation algorithms, and confirmation cycles to prevent false engagements. Extreme speed compresses these cycles. The faster the track evolves, the greater the demand on network latency and operator confidence. Around this point, reassessment becomes necessary. The limitation is not solely hardware performance, but institutional tolerance for rapid authorization. As speed increases, human oversight becomes the limiting factor. Operationally, automated decision support expands. Strategically, command chains face pressure to pre-authorize engagement rules, increasing escalation risk. A further reassessment emerges as speed dominance affects not just tactical engagements but operational planning. Traditional air superiority campaigns depend on shaping operations, suppression of enemy air defenses, and gradual erosion of defensive nodes. High-speed penetrators reduce the feasibility of phased approaches. If a platform can traverse defended airspace faster than a defender can react coherently, then denial strategies must shift from interception to preemption. The mechanism is temporal superiority. The operational effect is that defenders must attempt to neutralize launch platforms before they accelerate, relocating emphasis to basing and early warning infrastructure. Strategically, this redistributes vulnerability across domains. Air superiority as a concept has long implied control through persistent presence and the ability to contest any incursion. Speed alters this premise. A defender may retain numerical superiority yet fail to prevent episodic penetrations. Each successful penetration, even if limited in scale, erodes confidence in coverage. The cause is not invisibility, but inevitability of transit. The mechanism is overmatch in transit time. Operationally, this forces recalibration of sortie allocation and alert status. Strategically, it introduces ambiguity into deterrence calculations, as adversaries perceive exploitable windows.
Escalation control becomes more fragile under conditions of extreme speed. Decision-makers must interpret ambiguous tracks moving at velocities associated with both conventional and potentially strategic payloads. The compressed timeline reduces deliberation. The mechanism is cognitive saturation under time pressure. Operationally, this may result in premature engagement or hesitation. Strategically, miscalculation probability increases, especially in contested regions with limited warning depth. Planners and intelligence agencies respond to speed dominance by prioritizing earlier detection, distributed basing, and hardened infrastructure. Investments shift towards space-based sensors, rapid queuing systems, and autonomous tracking algorithms. Yet adaptation lags because doctrinal assumptions were optimized for stealth-centric threat models. Retraining operators, redesigning command hierarchies, and recalibrating engagement rules require institutional time. The cause is doctrinal inertia. The mechanism is structural dependence on legacy engagement sequencing. The operational effect is transitional vulnerability. The strategic consequence is a temporary imbalance that may persist longer than anticipated. Global balance implications must be framed through doctrine rather than speculation. States that achieve reliable high-speed penetration capability acquire a tool that complicates defensive planning disproportionate to its numbers. They need not dominate the airspace continuously. They must only demonstrate that denial is unreliable. The mechanism is psychological as much as kinetic. Operational planners confronted with uncertain interception success must allocate disproportionate resources to guard against low-probability incursions. Strategically, this redistributes deterrence weight toward the actor capable of compressing time. Speed destabilizes deterrence more than stealth because it alters the tempo of confrontation rather than merely its visibility. Stealth can be countered through sensor diversification and data fusion. Speed challenges the defender's ability to complete the engagement cycle at all. The cause lies in physics rather than signature management. The mechanism is time compression that reduces corrective opportunity. Operationally, defenses become reactive rather than anticipatory. Strategically, this undermines confidence in graduated response frameworks built on measured escalation. Future air wars under these conditions are likely to be defined less by sustained presence and more by episodic, high-velocity incursions designed to exploit compressed timelines. The decisive variable becomes not detection probability, but reaction sufficiency. States unable to accelerate their decision architecture will find their defensive depth functionally reduced, regardless of inventory. Adaptation will require restructuring of engagement doctrine around speed parity or preemptive positioning, neither of which restores the former balance fully. The cumulative assessment is not that stealth has become irrelevant, nor that missiles have ceased to function, but that the organizing hierarchy of air power attributes has shifted. When transit time becomes shorter than decision time, control of airspace ceases to rest solely on detection and shifts toward the ability to act before comprehension stabilizes. That transition reorders strategic calculus in ways not yet fully integrated into planning models. Airspace control was once defined by who could see first and shoot first. It is increasingly defined by who can traverse before the defender can complete a decision cycle, and that condition cannot be reversed by incremental upgrades within existing doctrine.
The implications of this transition extend beyond engagement mechanics into the architecture of campaign design. When speed becomes the dominant attribute, campaign sequencing loses some of its traditional meaning. Historically, air campaigns unfolded through identifiable phases: initial suppression of air defenses, degradation of command nodes, establishment of air superiority, and subsequent exploitation. Each phase depended on cumulative pressure and attrition. Extreme speed disrupts this layering. Cause precedes mechanism. A high-velocity platform can traverse defended airspace before suppression effects mature. The mechanism is the decoupling of penetration from sustained air dominance. The operational effect is that limited objectives can be achieved without full-spectrum air control. The strategic consequence is that defenders may experience operational shock without prior warning indicators associated with large-scale campaign preparation. This shift forces reconsideration of the relationship between offensive and defensive investment. Missile-centric defenses are capital-intensive and designed for persistent denial. If speed reduces engagement reliability, the marginal utility of each additional battery or interceptor decreases against specific threat classes. The cause lies in diminishing engagement windows. The mechanism is reduced intercept geometry viability at extreme closure rates. Operationally, defenders must increase redundancy or accept episodic penetration risk. Strategically, resource allocation models become strained, as cost-exchange ratios no longer guarantee advantage through scale alone. Command and control structures are particularly vulnerable to temporal compression. Air defense doctrine presumes that information flows upward for validation before engagement authority is exercised. Speed shortens the interval between initial track detection and terminal impact or exit. The mechanism is decision latency exceeding threat transit time. Operationally, engagement authority must migrate downward or become automated.
Strategically, this erodes centralized oversight and increases reliance on machine-assisted or pre-delegated response. The structural change is not technological alone, but institutional, as civil-military command relationships adjust to reduce deliberation windows. The interaction between speed and geography introduces additional imbalance. States with limited strategic depth face disproportionate exposure. When a high-speed platform can traverse national airspace in minutes, early warning radars positioned near borders provide minimal reaction time. The cause is geographic compression amplified by velocity. The mechanism is near simultaneity of detection and overflight. Operationally, air defense must be layered inward rather than outward, reallocating assets from perimeter coverage to central nodes. Strategically, smaller states become more reliant on alliances or forward deployment to compensate for intrinsic depth limitations. Energy asymmetry remains central. A platform entering defended airspace at high altitude and high Mach retains substantial kinetic energy, enabling rapid exit even if engagement is attempted. Missiles launched from lower altitudes must expend energy climbing before maneuvering. The mechanism is initial state advantage. Operationally, interceptors may expend significant fuel or missile inventory for low-probability engagements. Strategically, the offense benefits from a favorable cost exchange dynamic in terms of sortie risk versus defensive expenditure. Airborne early warning systems, long considered force multipliers, also encounter limitations under speed dominance. Their detection range may be sufficient, but queuing interceptors within compressed timelines becomes challenging if fighters are not pre-positioned. The cause is mismatch between detection range and intercept readiness. The mechanism is that sensing does not equate to intercept geometry viability. Operationally, continuous combat air patrols at forward positions become necessary, increasing maintenance cycles and pilot fatigue. Strategically, sustainability of persistent coverage becomes questionable in prolonged crises. Missile development pathways reveal structural lag. Incremental improvements in secret sensitivity, propulsion efficiency, and data link resilience extend engagement envelopes, but they do not eliminate the fundamental constraint imposed by time. Each improvement yields diminishing returns when target velocity approaches or exceeds engagement design assumptions. The cause is approaching physical performance ceilings. The mechanism is that guidance correction intervals and control surface authority cannot scale indefinitely without proportional increases in mass or complexity. Operationally, missiles become more expensive and less numerous. Strategically, reliance on them as primary denial tools becomes precarious against specific high-speed profiles.
At the doctrinal level, speed dominance compels reconsideration of deterrence signaling. Traditional deterrence messaging relies on visible defensive capacity, layered systems, interceptor squadrons, radar networks. These assets project denial credibility. If adversaries calculate that specific high-speed incursions are likely to succeed, even sporadically, perceived denial credibility weakens. The cause is observable kinematic overmatch. The mechanism is erosion of confidence in interception probability. Operationally, defenders may attempt to compensate through public demonstration of new countermeasures. Strategically, the signaling environment becomes ambiguous, as demonstration may not translate into actual restored reliability. Escalation stability becomes increasingly sensitive to misinterpretation. High-speed platforms reduce the interval between launch detection and impact estimation. In regions where strategic and conventional delivery systems share similar velocity profiles, ambiguity intensifies. The mechanism is overlapping kinematic signatures. Operationally, early warning systems may generate alerts that require immediate classification under compressed timeframes. Strategically, the risk of worst-case assumption increases, particularly where communication channels are strained or political trust is limited. Planning paralysis can emerge not from technological inferiority alone, but from uncertainty about response efficacy. When defensive planners cannot model reliable intercept outcomes against high-speed threats, contingency plans multiply without clear prioritization. The cause is probabilistic unpredictability. The mechanism is reduced confidence in deterministic engagement modeling. Operationally, forces may be dispersed to hedge against multiple scenarios, diluting concentration. Strategically, adversaries capable of sustained high-speed operations gain initiative by imposing planning complexity disproportionate to their numerical strength. Historical analogy reinforces the gravity of tempo shifts. In previous eras, transitions in speed, from propeller-driven aircraft to jets, from subsonic cruise to supersonic strike, forced rapid doctrinal revision. Those transitions, however, occurred alongside predictable warning and intercept margins. The current shift compresses margins to a degree that challenges institutional adaptation cycles. The cause is exponential rather than incremental increase in transit velocity. The mechanism is structural mismatch between technological acceleration and doctrinal revision pace.
Operationally, training and procurement cycles struggle to synchronize with threat evolution. Strategically, imbalance persists through transitional periods longer than political timelines anticipate. Intelligence assessment processes are similarly affected. Threat evaluation traditionally integrates observed performance, testing data, and modeled engagement scenarios. When speed becomes the primary variable, modeling assumptions must account for narrower reaction intervals and higher uncertainty in mid-course updates. The cause is sensitivity of outcomes to minor timing discrepancies. The mechanism is that small errors in detection timing produce disproportionate changes in intercept feasibility. Operationally, intelligence confidence intervals widen. Strategically, policymakers must act under increased ambiguity regarding both capability and vulnerability. The relationship between speed and survivability alters risk calculus for offensive planners. A high-speed platform may accept higher signature exposure if transit time ensures reduced engagement opportunity. The cause is trade-off between detectability and reaction sufficiency. The mechanism is prioritization of velocity over signature suppression. Operationally, design philosophy shifts towards structural resilience and propulsion performance. Strategically, this reorders procurement priorities and alliance interoperability considerations, as partners must adapt to new threat profiles. Adaptation pathways for defenders exist but are constrained. Forward basing to reduce intercept distance improves reaction time but increases vulnerability of those bases. Space-based sensors extend detection depth but require secure data relay under potential electric attack. Autonomous engagement systems accelerate decision cycles but raise control and accountability concerns. Each adaptation addresses mechanism but not root cause, velocity exceeding doctrinal assumptions. Operationally, layered mitigation may restore partial reliability. Strategically, complete restoration of prior engagement certainty appears unlikely without fundamental rebalancing of speed parity. Global balance implications become evident in regional flashpoints where strategic depth is limited and airspace contested. Actors capable of fielding credible high-speed penetration platforms introduce uncertainty disproportionate to their fleet size. The cause is asymmetry and temporal advantage. The mechanism is that even a small number of sorties can stress defensive networks calibrated for larger, slower formations. Operationally, defenders must treat each incursion as potentially decisive. Strategically, crisis stability erodes as even limited operations carry amplified psychological and operational weight. Deterrence theory traditionally balances capability, credibility, and communication. Speed dominance alters all three. Capability is enhanced not solely through destructive potential but through assured transit. Credibility shifts from promise of response to capacity for immediate presence. Communication becomes compressed as actions unfold faster than diplomatic channels can process. The cause remains temporal superiority. The mechanism is the narrowing gap between intent and effect. Operationally, signaling through maneuver becomes less controlled. Strategically, thresholds for escalation become blurred. The structural change is therefore not confined to hardware performance. It represents a shift in the temporal foundation of air warfare. When engagement cycles cannot be completed within the transit window of an adversary platform, the defender's architecture is forced into reactive posture. Reactive posture, sustained over time, erodes deterrence credibility and planning coherence. The cumulative strategic consequence is not dramatic collapse, but gradual recognition that established control measures no longer guarantee exclusion. In this environment, the hierarchy of air power attributes has been reordered. Stealth remains relevant for survivability in contested environments, yet it no longer singularly defines advantage. Speed, by compressing decision time below defensive reaction thresholds, exerts systemic pressure across tactical, operational, and strategic layers simultaneously. The shift is rooted in physics and manifested in doctrine. Once transit time falls below decision time, the balance of initiative shifts irreversibly towards the actor who can move faster than systems designed to respond.
The consequences of this shift become most pronounced when examined through the lens of escalation management rather than platform performance. In prior doctrinal models, escalation could be moderated through calibrated visibility. Stealth operations allowed selective signaling, presence without detection, or detection without attribution. Speed alters this equilibrium. A high-velocity penetration provides minimal interpretive space between detection and outcome. Cause precedes mechanism. When a platform traverses defended airspace in minutes, the defender must interpret intent and decide response in near simultaneity. The mechanism is elimination of observational pause. The operational effect is compression of escalation decision-making into the same temporal window as tactical engagement. The strategic consequence is erosion of graduated response frameworks. Escalation stability depends on clarity of thresholds and sufficient time for verification. Speed reduces both. Early warning systems may detect an incoming object at extreme velocity, but lack sufficient data to determine payload or mission profile before critical nodes are threatened. The mechanism is insufficient classification time relative to transit duration. Operationally, defensive commanders may adopt pre-authorized engagement policies to compensate. Strategically, this increases the probability of unintended confrontation, particularly in regions where multiple actors operate overlapping airspaces. The deterrence equation shifts accordingly. Traditional denial strategies aim to convince adversaries that penetration will fail.
When speed makes interception uncertain, denial credibility weakens. The alternative deterrence model, punishment after penetration, places emphasis on retaliatory capability. However, if high-speed platforms can strike and exit before attribution stabilizes, even punishment-based deterrence becomes complicated. The cause lies in asymmetry between action speed and attribution speed. The mechanism is that political confirmation processes lag behind physical events. Operationally, retaliatory planning becomes more complex. Strategically, ambiguity favors the initiator of high-speed operations. Planning institutions are structurally conservative by design. Procurement cycles, training programs, and doctrinal publications reflect years of iterative refinement. Speed dominance imposes a requirement for rapid doctrinal revision that institutions are not optimized to execute. The cause is velocity exceeding adaptation tempo. The mechanism is misalignment between technological development cycles and bureaucratic processes. Operationally, interim measures proliferate: temporary deployments, adjusted alert levels, experimental task forces. Strategically, such measures signal awareness but not resolution, reinforcing the perception of transitional imbalance. Air superiority doctrine traditionally assumes that control of airspace is achieved through persistent presence in layered denial. Speed introduces episodic control. A defender may maintain routine patrols and active radar coverage, yet a high-speed incursion can puncture that control without sustained engagement. The cause is nonlinearity between presence and interception probability. The mechanism is that continuous coverage does not equate to continuous engagement opportunity when transit windows are brief. Operationally, airspace control becomes conditional rather than absolute. Strategically, adversaries can exploit conditional gaps to achieve discrete objectives without triggering full-scale confrontation. Alliance structures are also affected. Collective defense arrangements often distribute sensor, interceptor, and basing responsibilities among partners. If speed compresses reaction time below coordination thresholds, multinational response becomes difficult to synchronize. The cause is interdependence under temporal pressure. The mechanism is latency in cross-border data sharing and political authorization. Operationally, national forces may act independently rather than collectively. Strategically, alliance cohesion faces stress precisely at the moment rapid coordination is required. The intelligence cycle must adjust to new warning indicators. Under stealth-dominant paradigms, emphasis rested on signature detection and pattern analysis of gradual buildup. Speed-dominant threats may require emphasis on launch readiness indicators, propulsion testing, and basing posture rather than airborne signatures alone. The cause is reduced utility of in-flight detection. The mechanism is that pre-launch indicators gain importance when post-launch reaction time is insufficient. Operationally, intelligence agencies must prioritize predictive analysis. Strategically, misjudgment of readiness could lead to surprise despite technical awareness of capability. Economic considerations reinforce imbalance. High-speed platforms are costly to develop, but they can impose disproportionate defensive expenditure on adversaries. Each incursion may compel activation of multiple interceptor squadrons, missile launches, and elevated alert levels across wide sectors. The cause is defensive redundancy requirement. The mechanism is cost asymmetry between limited offensive sortie and distributed defensive response. Operationally, sustained high-speed pressure can strain readiness budgets. Strategically, prolonged imbalance may influence broader force structure decisions. The psychological dimension cannot be dismissed within a strategic assessment. Confidence in air defense systems underpins both civilian assurance and military morale. Repeated demonstration that certain platforms cannot be reliably intercepted alters perception even if physical damage is limited. The cause is visible penetration despite defensive density. The mechanism is perception of vulnerability amplified by speed spectacle. Operationally, this may drive accelerated modernization programs. Strategically, it influences political resolve and public support during crises.
Adaptation pathways will focus on restoring temporal margin. This may include forward-deployed interceptors, improved propulsion for defensive missiles, or autonomous tracking systems with reduced human latency. Yet each adaptation competes with resource constraints and organizational inertia. The cause remains structural. Physics has shifted the engagement baseline. The mechanism is that incremental upgrades struggle to overcome exponential closure rates. Operationally, adaptation will likely be uneven across regions and actors. Strategically, imbalance will persist wherever adaptation lags. The broader doctrinal implication is that airspace can no longer be conceptualized as a static domain secured by layered coverage. It must be understood as a temporal domain, where control is measured in seconds rather than sectors. Speed converts distance into time compression, and time compression into strategic leverage. Cause leads to mechanism. When distance ceases to provide reaction buffer, the defender's planning assumptions require revision. Operationally, air defense transforms from territorial denial to rapid response competition. Strategically, this alters the calculus of both deterrence and compellence. In the long term, equilibrium may re-emerge through speed parity or new defensive paradigms. However, equilibrium reached under compressed timelines will differ fundamentally from the stealth-centric balance of previous decades. Control will depend less on invisibility and more on temporal dominance across detection, decision, and engagement phases. The actor capable of aligning propulsion, altitude, and command acceleration will hold disproportionate influence. The structural warning is therefore clear. Airpower doctrine built on the premise that detection precedes decisive action is no longer universally valid. When transit time approaches or undercuts decision time, the defensive architecture designed for layered interception becomes inherently reactive. In such an environment, assurance of denial cannot be guaranteed through density alone, and the stability once derived from predictable engagement cycles begins to erode at its foundation.
Airpower doctrine was constructed on the premise that detection creates opportunity, and that opportunity creates control. Speed has disrupted that sequence. When a platform can traverse defended airspace faster than defensive systems can complete detection, authorization, and interception cycles, layered denial ceases to guarantee exclusion. The imbalance is not temporary and not confined to a single platform class. It is structural, rooted in physics, and reflected in doctrine. Control of airspace is shifting from those who can hide to those who can compress time beyond the defender's ability to respond.